From today we are going to start a new topic, which is again closely related to the rotational motion. Okay? In the sense that now, rather than considering motion of a rotating object, we are going to look for the effect of rotation of the reference frame itself or the coordinate frame itself, right? And see how we can analyze systems there. So in physics, our understanding of the state of nature comes from measurements and observations. Right? And these in general depend on the frame of reference of the observer. Right? So any experiment that you perform will give a result which is implicitly connected with the frame of the observer. Right? Okay. Now the reference frames in this sense are basically of two types. One is termed as an inertial reference frame, and the other one is a non-inertial reference frame. Okay. Now, evolution of any system. So let's start with these two reference frames. So, So the reference frame could be either inertial, okay, or non-inertial. Right? And the way we define this inertial non-inertial is in terms of evolution of a system. Right? So now the evolution of any system is governed by our governing equation of motion, which is then F equal to ma. Right? So this is the equation of motion in general. And then we also wrote it down for the rotational motion. But anyway, right now we are not interested in that distinction between translation and rotational. So the evolution of any system, so especially when we are dealing with the motion, right? We are not worried about other physical process. So the evolution of any system in that sense is then governed by this equation of motion, F is equal to ma, right? Where this F in this equation represents the physical interaction present in the system, right? And we know that there are four kinds of physical interactions. So this is a representation of the physical interaction, right? And in nature we have four fundamental interactions, and sometime I think in one of the lectures we discussed this. So gravitational, electromagnetic, strong, nuclear, and weak nuclear. Right? So these four fundamental interactions, and these are the ones which are then forming the total or part of this force in this equation. And this ma, so the acceleration, right? Our acceleration term is then representative of the change in state of the system, right? So, and we call it as force applied on the system is equal to the acceleration given to the system, right? Which is strictly true. I mean, which is at least as long as we are discussing motion of a system, be it translation, be it rotational, is strictly true, right? Okay. Now, and in this way, when we write down this governing equation, what we are saying is that acceleration of a system or the rate or the evolution of the system, the change in state of the system, is directly proportional to the force or the physical interaction responsible for that change, right? And they are connected by a proportionality constant, which in normal sense we define as mass. Right? So mass, at least for this discussion, is nothing but the proportionality constant for this governing equation m, and as we will see soon, when used in this equation, this mass is also termed as inertial mass, right? Or basically the proportionality constant which is connecting the acceleration of the system to the force, which is connecting the motion of the system with the physical interaction, right? Okay, so this is the definition of this governing equation, right? Now, with this information, we can describe or we can try to define what are inertial and what are non-inertial frames. So an inertial frame is one in which the acceleration of the system comes solely due to the physical nature or the physical forces present in nature, right? So in a frame, in a coordinate reference frame, where change in state of system is only because of one of these four fundamental forces of nature, fundamental interactions in nature, then that frame is called an inertial frame, right? So this is actually connecting the physical interaction with the reference frame, right? And it happens to be the case that all frames which are either stationary or moving with a uniform velocity, with a constant velocity, with respect to an inertial frame. So let's say I know that I have one frame of reference which, let's say to begin with, is inertial. Then any other reference frame which is either stationary with respect to the first one or is under uniform motion with a uniform velocity, particularly with respect to this inertial frame, will also be inertial, right? Okay. Once we say this, now what I can do is I can also make another statement. So we have knowledge about all these things. You have learned this earlier also. We're just trying to put it in a different way. So once we have defined what is inertial frame, implicitly what we are also saying is that uniform or motion with uniform velocity, with constant velocity, is not considered as evolution of the system. It's not change in state of the system. In fact, rather, as we say, being stationary or being moving with uniform velocity is more or less the same. It's exactly the same thing, not more or less. It's exactly the same thing because the two frames are inertial frames, and we cannot, as long as, and we'll show this soon, as long as looking at a particular phenomena in these two reference frames, we cannot distinguish which one is stationary and which one is moving, right? So motion or rather change in state will be described or will only be defined when the system has an acceleration. A uniform velocity motion is as good as the system being stationary in terms of effect of these fundamental interaction or the forces, right? Okay. Now, an implication of this is stating the inertial frame like this is the constancy of laws of nature, right? And what is the law of nature? F equal to ma. Ma is the change in state. F is one of these four fundamental interactions. So it's a constancy of laws of nature in all inertial frames, right? And the way we say it is that measurements performed in one inertial frame are equivalent, or basically they are going to give the same results if you perform them in any other inertial frame, right? So different inertial frames are exactly equivalent to each other, right? The measurement performed there will give you the same result or the same inference. Okay, so far so good for those, or so much for the inertial frames. Now, once we define the inertial frame, now we can start defining, or now we can try to define what is a non-inertial frame, right? And a non-inertial frame is one in which is accelerating with respect to an inertial frame, right? So, because all the frames which are constant in relation to one of the inertial frames or moving with uniform velocity are also inertial, but if there is relative acceleration, then one of the reference frame is going to be non-inertial, and of course we'll always take one as a reference, inertial reference frame, stationary, in which all the phenomena happens as we understand it, and then we look at different the other frames of reference, be they inertial or non-inertial, right? Now the acceleration of the reference frame, and this is what we will show in today's lecture. The acceleration of a reference frame, right, results in measurements. Again, because we are trying to understand laws of nature, and this can only be understood if you perform a measurement or if you do an observation. So the acceleration of the reference frame results in measurements which cannot be explained completely by these four fundamental interactions, right? And require additional information or require additional forces to satisfy this equation, right? And these forces are then in the non-inertial frame, these are termed as fictitious forces. So inertial are let's say fundamental interactions. Non-inertial, sometimes also known as accelerated frames of reference or reference frames. Right? So this will have fundamental interactions, plus additionally there will also be effects which seem fictitious to us, so they are called fictitious, and that is the effect of the acceleration of the frame of reference. Right? Okay. So now what we can do is we can look at the same concept using or in a more mathematical way, which is useful to bring out the point that we just discussed. Right? So let us see the relation between inertial and non-inertial frames. Right? Okay. So what we do is we look at this relation. However, at least for the time being, for the sake of this discussion, I am going to look at this relation with certain extra restrictions, and those restrictions are that mass, and now the inertial mass, space or the coordinates x, y, z, and time, right, they are equivalent in all frames, be them initial, be the frame be inertial or non-inertial, right? So, and the reason for this will probably be clear in future, like after a couple of lectures. But for time being, we are not going to worry about the mass, space, and the definition or the nature of mass, space, and time in these different reference frames, right? So with this restriction, let us see the relation between inertial and non-inertial frames, right? And for that, let's start with, let's say we have an inertial frame. So let us depict it. Let us try to represent it. So this is, let's say, my inertial coordinate system, right? And I'll call this a frame O with x, y, z coordinates, and then the way we used to do it. I cap is unit vector along x, j cap is unit vector along y, and k cap is unit vector along z. Right? Okay. Let us take a point particle here or a point here, call it P. Right? And now to describe the state of the system, what we need is the position vector of the system in this coordinate frame. So let us say O is your inertial frame, right? Where frame and a point P has position vector, let's say R, right? Okay. So this is my system, and now I take another reference frame. Let's say that's also inertial, so O prime, right? Again, inertial, and moving with constant speed V prime, right? With respect to O. Okay? So this is the information that's available. Let us try to see what could this O prime be. So let me draw the O prime. Okay. This could be my O prime at any instance, right? So let's say the instance that we are looking at the position vector of this. This is O prime. Okay. So O prime with the origin at O prime, x prime, y prime, z prime are the coordinate axes for this. And the way I am going to plot it, draw it here is I am keeping the orientation same. But we also know that the coordinate or these different frames can be arbitrarily oriented about each other, and we also know that relation, right? I wrote down the rotational matrix or rotational transformation matrix if for coordinate rotation, so that's not a concern. We can always do it in a more general way. So anyway, so now let's say this is my O prime frame, and now look at that very instance, what is the position vector of P in this reference frame? Right? So the point P does not change, right? And this could be then the position vector of P. So I'll write it here. Position vector of P is then R prime. Okay. Now we have taken one inertial. Let us take one non-inertial frame. Right? And now what will make it non-inertial is, so this is having with uniform acceleration, let's say A with respect to O, right? So O is my initial inertial frame, and that is the one which I am going to take as a absolute reference frame for time being, right? And it's going with acceleration A naught double prime, right? So let's try to define this also, right? And I'm just going to define it arbitrarily. So I can now define, let's say, another reference frame, and as I said, orientation will not matter, right? So origin at O double prime, Z double prime, X double prime, Y double prime will have its own unit vectors and all that, and will also have relationship between different the coordinate axis and the unit vectors, right? Now in this reference frame, then this is the position vector of that same coordinate point or the same physical system P, right? So we have this. We have some additional information about these two frames with respect to the frame O. One is frame O prime is moving with constant velocity with respect to frame O, right? So let's call its position vector in any given instance from O to O prime as let me call it as capital R prime, right? And similarly, at any given instant, I can also define a position vector between O and O double prime, where O double prime is actually accelerating with a uniform constant acceleration with respect to O, and let me call it as R double prime, right? Okay, so this is now my this is the relation which we have represented in terms of coordinate axis and the position vectors for these three reference frames, right? Okay. Now let us see. Now let us say that in my original reference frame O, there is a force or there is an interaction which is present for the system P, and the system is evolving under that force, under that interaction. So let us see what is the effect of that interaction. So now in O, if the interaction is F, then what we'll have is, and the mass of the particle is P, or the system is P, so this is simply d2r over dt square, right? This is the fundamental governing equation of motion, right, for the system. So this is the evolution of the system in reference frame O, right, where F is the physical interaction, and this is just the acceleration of the system of point P. Okay. Let's write it down as 1. Okay. What about O prime? So in O prime, if I am looking from O prime, right, then from the point of view of O prime, right, the force F prime is m d2r prime over dt square, right? And that's why while starting the analysis, I said that we'll assume the equivalence or constancy of nature of mass, time and space. So m is same in both reference frames, the definition of time is same, or the equivalency of time is same in both reference frames, right? We'll keep it. Only thing that changes is the position vector. And what is this position vector? Right? Now this position vector can be written in terms of the position vector r and relative position vector of the two origin, O and O prime. Right? So we can do this, which is nothing but m d2 over dt square, and r prime is simply r minus r. Right? And solve it further. d2r over dt square minus m. Okay. Now the second term is actually 0 because we said that O prime is moving with uniform velocity with respect to O. So that means there's a velocity here. So dy dt r is a constant, and then again its time derivative will be 0. So this term is 0, and if this term is 0, then this simply gives us m d2r over dt square, which from 1 is f prime is equal to f. That is 2. And looking at 1, we can say that the change in system, evolution of the system, is in frame O prime, which is moving with constant velocity with respect to our initial frame O, is exactly the same. And in this sense, all the frames which are either stationary with respect to each other or moving with constant velocity, right? And one of them is inertial, then all other frames are also inertial, right? So the way of saying the same thing is that forces experienced in that moving frame with constant uniform velocity are exactly the same as if we are measuring it in a stationary inertial frame. So f prime is same as f, and this also then says that f prime is exactly same as the physical interaction that are present for that system. So far so good. Let's look at the same thing in O double prime now, right? We'll do the exact same analysis. So with respect to O double prime, it's a change or rate of change of this position vector, right? To look at the state of P, that means F double prime is nothing but, and we said that mass is same, time is same, so R double prime over dt. And what is R double prime? R double prime again is R minus capital R double prime. So m d2 over dt square R minus capital R double prime. This again gives us m d2r over dt square minus m d2r double prime over dt square. This is f from 1. So f double prime, the interaction or the force in, or basically the change in state of system P, point P, as seen from this accelerated frame O double prime, is equal to the force or the change in state as would have been seen in an initial frame minus m, right, and d2r double prime over dt square, right. So the rate of acceleration of O double prime with respect to O, which is now not 0 because O double prime is a non-initial frame. So A. So what we see is in inertial frames O prime, nature of force does not change. In non-inertial frame, as far as the observation is concerned, as far as the measurement is concerned, right, we not only have the physical force F, which comes from the physical interaction, and we know that there are only 4 types of these physical interactions, so one of those interactions, but we also have a term which again has dimension of force because it's still mass into acceleration, and that is what is the dimension we assign to force. So it's still some kind of a, well, it's a number which is equivalent to force, it's a quantity which is equivalent to force, right, and depends on the acceleration or the reference frame. This is actually written as the fictitious force. So this is F, which now I'll call, let's say, physical, because it has physical origin, it is coming from the physical interactions, 4 fundamental physical interactions, plus F fictitious, right? So this acts as a force, but it doesn't have a physical origin. So it's fictitious in that sense that one would feel in an accelerated frame, one would feel as if not only this, there is another force acting on the system, right? However, its origin is not one of the 4 fundamental forces. Okay? So then this is the effect of the frame being non-inertial, and here again the fictitious force is defined as, so if you look at this, then minus m a double prime o naught. So it's related to, or it's in the opposite direction as the, especially in this case, as the translation acceleration, right? So the frame is accelerated in one direction. Any measurement in that frame would seem as if there is an extra force which has the same magnitude acted in the opposite direction, or against the direction of motion. Right? Okay. So this is then the analysis which clearly shows the exact same concepts that we discussed in case of for inertial and non-inertial frames. A small remark again, just to re-emphasize the same thing, is that we call this force as F fictitious not because it doesn't have an effect. In terms of measurement, in terms of effect, it's a real force, right? It will have measurable effects in the accelerated reference frame. However, we call it fictitious only in the sense that the origin of this force is not because of one of the 4 fundamental interactions, right? It's purely kinematic. It purely comes because of motion of the system, not because there is a fundamental interaction in the system.